A little bit more on solving systems of equations by elimination when we have 3 variables, 3 equations. This time it's the odd cases. How do I know when I have no solution or infinitely many solutions? I hope you've gone to the other video that I pointed you to, because I'm not going to try to draw the 3-dimensional planes, but I think it really helps when you're trying to figure out what's going on. Why do we get no solution? Why do we get infinitely many? So I'm just going to super quickly do it. I will do the 2-dimensional recap. So a quick recap. When do we get no solution on 2x2s? Is when we have parallel lines, lines that don't intersect. So when we have 3x3s and we're dealing with 3-dimensional, that means we have 3 planes. Now 2 of them may intersect, but they don't all 3 intersect. So if you go to the other video, he gives some visuals on that. Infinitely many, when we're doing 2x2s, 2-variable linear equations, then infinitely many means it's just the same line, right? One's just wearing a costume. So if we keep that in mind, that might help us with our 3x3s. Here we have 3 equations with 3 variables, and even as I copy them down, I notice these two have some similarities. Right? Not looking at the constants, don't pay attention to those yet, but notice that this one, the blue one, is 2 times the red one on the x and on the y and on the z. So if I started to do elimination, and I'm just going to do this real quick, if I do elimination, I'm going to write the blue one, 2x plus 2y minus 2z equals 6. If I take the red one and multiply by -2, I'm going to get -2x minus 2y plus 2z equals 4, -4. So I have to do my checking. You can tell I'm pausing because I'm looking at my signs. My blue original, positive, positive, negative, positive. Blue copy, positive, positive, negative, positive. Red original, positive, positive, negative, positive. Switch the signs, negative, negative, positive, negative. And I can just hear that sing-songiness of the signs in my head. So I just got to remember this guy's negative. All right, so if I go to do elimination, my x's drop out, my y's drop out, my z's drop out. It's just like a system of 2 variables, 2 equations. I get something that's not true. That is not true. So it's no solution. Now there might be a solution to 2 of the 3, but there is no solution to the system of all 3. So 2 of them might be parallel, or they might intersect in that triangle the way it was described on the other video. But as far as the whole system goes, there's not something that they all share. So that's why it's no solution. You don't have to worry about that third one at all. If you get no solution on 2 of them, if you get 2 of them where you get that false statement, it's no solution. So when you're writing them down before I switch to a new problem, it makes sense to watch for something, like to look for those similarities, because you're going to save yourself a bunch of work. If you would have gone to work with the green and the red and started eliminating, y's or z's or something, then you would have, sure, you would have gotten one equation that has 2 variables, but then the next time, you can do a bunch of work that you don't need to do. So I highly recommend you look at the characteristics of the equation before you proceed. Here we've got another system of 3 equations with 3 variables, and they have a lot of commonality. If you just look, the red one and blue one are almost the same with one little change. The green one is almost 2 times the red one with one little change. So they just look awfully similar. So let's take a look at those. And looks like I'm going to prefer to get the z's to drop out. So I'm going to start with the red and the blue because that's going to be way easy. All I have to do is copy them down to get things to drop out. So x plus y plus z equals 3. And then I just have to copy the blue one as is. X plus y minus z equals 3. So way easy to get the z's to drop out. We've got 2x plus 2y equals 6. All right, that's a nice equation to deal with. And then if we do the same thing with the green and the blue, again, we don't have to do any multiplying. So to get my green, I'm going to do just copying it over, 2x plus 2y plus z equals 6. And I'm just going to copy my blue one as is, just right as it was again, because it'll let my z's drop out. X plus y minus z equals 3. So we've got 3x plus 3y equals 9. All right. Wow, those are pretty equations. So if I want to get something to drop out, I'm going to have to multiply one of those by a negative and turn all the coefficients into 6's. So I'm going to multiply this one by 3 and get 6x plus 6y equals 18. And I'm going to multiply this purple one by negative 2. So negative 6x minus 6y equals negative 18. Just as before, the indication that it's infinitely many is that we get a true statement. And if you're doing elimination, that generally means everything drops out. This is true, so it's infinitely many. Anything that'll solve one will solve the others. So you see on 3 by 3s, those odd cases, the no solution infinitely many, it's the same reasoning. It's almost just sometimes easier to see it, or at least maybe it's not that it's easier to see it, but it's within your best interest to try to see it without doing a whole bunch of work.